Okay, so let's welcome to homework 2 of Transport Phenomena 1. Where in this video we're going to be exploring the situation of a vessel, a closed vessel with a small hole punctured on the side. Okay, and the question at hand here is, well, what if we graph the function of the height of the liquid as a function of time? Well, it's going to look something like this. You'll notice that eventually it does reach steady state. So the question is, at what point, what height is that steady state, given a couple parameters? And we define a few variables here in our drawing. We have a vessel of height big H, which has a fluid level of H, little h, which is dynamic, which will change over time. Our hole has some small area, and we have a cross-sectional area of the vessel. Okay? And we're going to answer this question by creating a differential equation. And we'll create this differential equation with two rather simple topics in chemical engineering, one being Bernoulli's equation, and the other being the so-called equation of continuity. Equation of continuity. And while that sounds fancy, the equation of continuity is very simple. It's simply a flow rate balance. It's saying what goes in must go out. Well, like in this case, there's nothing going in, but we define two positions, position 1 and position 2. And what the continuity equation is essentially saying is that, well, at position 2, we have a area of the hole multiplied by the velocity. So look at units here. We have meters squared multiplied by meters per second. That's meters cubed per second. So that's volumetric flow rate, right? So this must equal a cross-sectional area of the vessel multiplied by the velocity at 1. Okay, and we say something special here, which makes our lives a little easier. You notice that the area of C, the cross-sectional area, is far, far, far larger than the area of the hole. And because of that, while the velocity of the fluid flowing out of the hole is significant, the velocity of the fluid level going downwards is rather negligible. So this, we can call this something very small, in other words, 0. We can call that 0. Okay? So then let's go on with that in mind. Let's go off and write down our expression for Bernoulli's equation. And it's defined like so. V2 minus V1 over 2. And these are squared terms. Plus Z2 minus Z1 over, multiplied by G. Okay? And this is equal to the value for frictional heating. Okay? Where frictional heating is equal to the internal change in energy minus the change in enthalpy. And since this is a system that's essentially open to the atmosphere, there's no change in internal energy and no change in enthalpy. So frictional heating is 0. Okay? And again, we discussed earlier that the velocity at position 1 is 0. So let's go off and look at this term here, the G term. We can either, this is rho gh, right? We can either we can view the position 2 as 0, or we can view position 1 as 0. So we ask ourselves the question, what makes more sense? Because we can do both, but one will land us in a heap of trouble and the other will not. The way we can answer that is, well, does it make sense to make position 1 0 at all? Unfortunately, position 1 will change with time because the fluid level goes down, while position 2 remains constant. So it would make more sense to call Z sub 1h height of the fluid level, and call Z sub 2 0. Okay? So we say that this is minus gh h. Okay. Here we have the value plus v2 squared over 2. Now we have to take care of our pressure term. Okay. Let's go off on a quick tangent and explain the idea of pressure recovery. Okay, and this is how we define P2. The pressure, we have to ask ourselves, what's the pressure at position 2? It's tempting to just say, oh, it's open to the atmosphere, it's pressure of the atmosphere. But you need to understand why that is. And that's because of the question of, do we have pressure recovery or do we not? So for a gradual expansion of a pipe, and we call this position 1 and position 2, we have some kinetic energy here, and when you expand the pipe, slow gradual expansion, this goes to a low kinetic energy. Okay? And you know by conservation of energy, where does that energy have to go? It has to go to some form of potential energy. Well, we're not changing height from position 1 and position 2, so where is that potential energy? It just so happens that pressure is a form of potential energy for fluids. So the pressure at position 2 is higher than pressure at position 1, and this is called pressure recovery. However, for a sudden expansion, just like our hole here, we're going from a small cross-sectional area to a infinite one. This is a sudden expansion. For a sudden expansion, there is no pressure recovery. No pressure recovery. So we say that the pressure at 1 is equal to pressure at 2. In other words, the pressure here is equal to the pressure of the environment. Okay? So that tells us that pressure 2 is PATM. Okay? Pressure 1 is a bit more of a beast to handle. We had mentioned that this vessel is closed. Okay? We call this area in a vessel the headspace, the vapor area, the headspace for a closed vessel. Okay? If this was an open top container, the question would be rather easy because it's open top, pressure at 1 is equal to pressure ATM. However, that's not the case here. We have to ask ourselves, well, if the height is lowering, the volume of this headspace is increasing, right? And because this is a closed area, since volume is increasing, our pressure should be decreasing with time. So in other words, pressure at position 1, P sub 1, is a function of little h. So that's what we're looking for. Okay? And what we use the ideal gas law here, and this pivots around one integral concept. Because this is closed, moles of gas remains constant. Okay? But what is moles of gas? We can find a numerical value for that. Moles of gas. So N equals P V over R T. Okay? But what's P? Well, you can say that the initial pressure here is atmospheric pressure. ATM. Makes our lives rather easy. How about V? Volume. Well, volume can be split into terms of cross-sectional area multiplied by H. Okay? So what is that though? So we have AC multiplied by big H, because that's the difference here, the difference right there, minus initial little h, the initial height of the liquid. So we now have an expression for N. Let's go off and use the ideal gas law again to derive for a function of pressure, P sub 1. Okay? So P, do I have enough room here? Good. P sub 1 equals to what? P equals N RT over V. Okay? In other words, N RT, we split apart that volume that volume expression as, again, cross-sectional area multiplied, in this case, by just h. Okay, h is our independent variable here. It's dynamic and it's changing. And you look here and you say, hey, I can plug that in right there. And what happens? Well, our t's cancel. Okay, our cross-sectional area cancels. And what are we left with? We are, and our r's cancel. So now what? We have P1 is equal to atmospheric pressure multiplied by H minus HI over, I just realized I misdefined that variable. This should be this height right here, which is changing. So it's big H minus little h, big H minus little h. Okay. So this is, well, over big H minus little h. Okay. This is our expression for P sub 1. So therefore, we can go ahead and finish our Bernoulli's equation here. Okay, so we define Bernoulli's equation as what? We have, what do we have here? We have, well, why don't I just write it out so we don't become confused? P2 is PATM, so P, let's do this in purple. PATM minus P1, our expression for P1, so PATM H minus HI over H minus H, right? All of that over rho. So what can we do? We can factor out PATM and rho. We now have P ATM over rho multiplied by 1 minus H minus HI over H minus H. Big H minus little h. Okay. Plus what? V2 squared over 2 minus GH equals 0. Now what are we solving for here? Maybe it's not so apparent now, so why don't we, before we answer that question, let's go off and find our differential equation. Okay? So we want to look for, let's look for flow rate at 2. So let's say Q, nope, that's a G. Q at position 2, so at the hole, is equal to what? The area of the hole multiplied by V2. Okay? Doesn't that look familiar? Right there, V2. What do we have here? V2. Check that out. But let's keep going here. We can define volumetric flow rate here as negative dV over dt. Okay, so this is where our differential equation comes in. Okay. But that's not quite good yet, right? Because we don't have, we have volume. So we can split that volume term as negative cross-sectional area multiplied by dH over dt. Ah, look at that. Look at that. We now have this expression here. A, the area of the hole multiplied by the velocity at position 2. Okay, so what's known here? This is known. That's known. Doesn't seem immediately obvious, but we have an expression involving this, that variable, right? And what do you notice about this? dHdt. Well, if you solve this differential equation, dHdt, that's going to get us a graph, a function of h as a function of time. So this is in fact the differential equation that we want to go off and solve. Okay, So now we have to find an expression for v sub 2, velocity at 2, okay? And that's just going to involve a little algebra. Just a little algebra. So what do we have? We're gonna have v2 is equal to positive gh, okay? Positive gh minus p atm over rho multiplied by the quantity 1 minus h minus hi over h minus h. Okay, so got that done. All of this multiplied by 2 and taking the square root of. Okay, so this whole expression, let's do that bigger. This whole expression is going to go in here. Okay, so at this point, it's always good to look at your independent variables and constants. So we have a differential equation we'll want to be solving. Area of the whole is a constant. Area cross-sectional area is a constant. Okay, that's a constant. H is our independent variable. Changes with time, right? Pressure ATM is a constant. Density is a constant. Big H, height of the vessel, is a constant. Initial height is a constant. Another independent variable. And this looks like a single variable ordinary differential equation. Okay, so there we have it. Next, we're going to go off into Python and use a numerical solver to go ahead and get our answer here. Okay, so now that we've derived our differential equation, we should go off and solve it in Python numerically, right? And just as a quick note, I did neglect to isolate our DHTT term in the last cut, but that's just a matter of 1 or 2 algebraic operations. Okay, so I'm not going to go over that. But we're going to numerically solve this differential equation by way of scientific Python integrate.solve IVP. And we've used it before in the past in MEB videos, but as a quick review, let's go over it. Solve IVP expects a function to solve, a time span to solve it over, okay, initial values, a method, and some other optional options. And it expects our function as a function of t and unknowns. And y is an array of unknowns because people who use solve IVP often use it to solve rather complex systems of differential equations. So there are multiple unknowns and there are multiple outputs. So the default solve IVP expects y as a array. Okay. So let's go off and create our right-hand side equation. So right-hand side, it takes in t and y. Okay. And let's see, y, our only unknown in this case is height. Okay. And it's array. Again, y is an array, so height is the first index in the y array. Okay. And it should also return a array. Okay. In this case, we only have one equation to return, and that's negative area of the whole multiplied by velocity at point position 2 divided by cross-sectional area. Okay, where velocity at position 2 is defined by this expression here. So v2 is equal to, you have to be extremely careful with parentheses here. Okay, you have to be careful and deliberate. Make sure not to make mistakes and make sure all of your parentheses get closed, right? H minus hi over h minus h minus 1, and check this out. Close, and close the square root. We're all good. So now we can go off and solve IVP. Oops. And take in RHS, that's the function that should solve, time span. Again, time span is expects it as a tuple, so from 0 to tn we have defined above as 10. That's completely arbitrary. Y naught is equal to initial height, right? And method, we're going to use a Bernoulli here. And we do want dense output so that it can intelligently create a accurate plot. Okay? And try it. Check this out. We do get an error, and I expected to get an error, right? If you recall, we expect our graph to look something like it drops a lot, and then it steadies out, and then it reaches a steady state where the height no longer changes. That's because you can think of it as the force of the pressure is no longer able to overcome the surface tension of the water. Okay, and if you read the error, array must not contain infinites or NaNs, and you notice that we have a square root function. Okay, and the square root function, you know that you cannot take the negative of the square root, so we must be generating a negative somewhere, and that we are generating a negative right here. What do we have here? Maybe it's easier to look over here. You have h minus hi. Both are constants. It always remains positive. But then here you have h minus big H minus h, right? And if this value becomes small enough, this then becomes negative, right? Then this whole value becomes negative. This whole value becomes negative. And that would make the value under the square root negative. So that's what we're trying to avoid. So let's say let's put np dot absolute value here. Okay. Hey, suddenly it works. Success is true. So let's try and go off and plot it. So fig equals make underscore sub plots fig dot add scatter, and we need to make it tplot equals np dot linspace 0 to tend, and let's do like, I don't know, 500 points in between. Oops. Add scatter x equals tplot y equals let's assign this to a value, assign this to an object. Let's call it I don't know, ht, height as a function of time. Okay, y equals ht dot sol, inputting in tplot. Believe we're all good. We're not good. What's wrong? What is wrong here? Oh, we need to I believe we need to grab the function. Yeah, we need to grab the first value in the output. So what do you notice here? It looks really wrong, doesn't it? Because again, I had told you that we know that it drops off sharply and then steadies out into steady state. But then it keeps dropping. That's not at all what we expected. Not at all what we expected. And that's because we threw in this absolute value here. While the math works out, at this point, the program is not intelligent enough to know where to stop, right? It sees this mathematical equation and it keeps going. So we want to know where steady state is achieved, okay? And this is where one of Solve IVP's features of events come in. Events, okay? And let's look at that. Events, okay? Events to track. So we can do a terminal event, and this is whether this tells the function to whether to terminate the integration if this event occurs. implicitly false if not assigned. So we want to define an event, right? Again, we would like to see whether or not this event goes to 0 right here. This mathematical equation goes to 0. So let's do that. Let's call this. Let's call this. Let's do v2 event. Okay. Takes in the same. This takes the same. This takes the same. What do you call it? The same format as RHS. Okay. v2 event, and we are returning. Well, before return, h equals y0, right? Return this because we want to figure out when this equals 0. Okay, and we want to assign this v2 event. Oops. One too many parentheses. I want to assign this v2 event a attribute of terminate. So v2 event that terminal. That's shoot. What's wrong here? What's wrong here? Maybe we should consult the what do you call it? Consult the documentation. Each function must have a signature event ty, so that we follow that and return. It should return a float. So indeed, we are returning a float. You can assign attributes like event.terminal equals true to any function in Python. Okay, that's why you should read the documentation. So let's do it. So v2 under event.terminal equals true. Hey, there we go. Perfect. So now we can use this function, this event of a function. You notice that if you read it here, the solver will find an accurate value of t where event t y of t equals 0 using our root finding algorithm. So it's going like what we wanted. It's going to find when this is 0 and it's going to stop the integration, right? So that way we can find, hey, where's the slope here equal to 0? Where are we reaching steady state? Okay. So let's go off and input this event. So in order to see what's going on, let's unassign that from that object. So let's do events equals, and again it expects a array, I believe. So events, list of callables. So v2 underscore event. What do we have? What do we have? You see, the solver has successfully reached the end of integration interval, right? And you see that success is true, and we have an event stored. And you should notice that this is an array of an array, and this event is time. At 4.59 seconds, this solver has found that, hey, this mathematical expression here is equal to 0. Therefore, we are at steady state, because the steady state, the word steady state means that all integrals of time equals 0. In other words, dh dt should equal 0 at this point in time, and we should stop integrating. So let's go off and do that here. So let's assign this to ht again. ht equals that, right? And we want to stop this at the event. So ht dot do you call it t events? Okay. 0. It should be 2 of them, because again, let's open up ht again. You notice that t events, this is an array within an array, or an numpy array within a Python list. So you have to index it twice to grab the correct value. So let's go off and do that. And we plot. And check it out. We now have an accurate plot for whenever this this system of a closed cylindrical vessel with this hole, it keeps leaking out until it reaches steady state because the pressure force is no longer able to overcome. It is no longer to be able to overcome the surface tension of the water. And this event will happen at 4.59 seconds. And the height, if this this liquid is water. If the water starts at 0.9 meters, this happens when the height reaches 0.89. Oh, okay. So that's part 1 of homework 2 done, and see you in the next video.